The transition elements have an unparalleled tendency to form coordination compounds or complex compounds. Complex compounds are those in which a central atom or ion is surrounded by a number of anions or neutral molecules possessing a lone pair of electrons. These surrounding anions or molecules are called ligands. Some examples of complex compounds are given here. They are pentamine cobalt 3 chloride, potassium ferricyanide 2 and nickel tetracarbonyl 0. The tendency of the transition metal ions to form complexes is due to their relatively small size and resultant high positive charge density. Presence of vacant n-1d orbitals. Their ability to show multiple oxidation states. Now let us look at the catalytic properties of these elements. Transition metals and their compounds are known to catalyze various reactions of industrial importance. The catalytic activity of these elements is attributed to their ability to exist in multiple oxidation states, which enables them to form unstable intermediate compounds. These metals also catalyze reactions by providing a suitable reaction surface. Familiar examples include the use of vanadium 5 oxide in the manufacture of sulfuric acid by the contact process. The use of finely divided iron in Haber's process for the manufacture of ammonia. And the use of nickel in the hydrogenation of oils. The table here shows the catalytic activity of some of the transition metals. Many views have been advanced to explain the mechanism of catalysis. In catalysis at a solid surface, bonds would be formed between the molecules of the reactants and the surface atoms of the catalyst. The 3d electrons of the first transition series elements are used in bonding, in addition to the 4s electrons. Thus, the concentration of the reactants at the catalyst surface increases, and the bonds of the reactant molecules weaken because their activation energy is lowered. Since the transition metal ions can change their oxidation states, they act as catalysts more effectively. For example, iron 3 catalyzes the reaction between iodide and persulfate ions by changing its oxidation state. It first gets reduced to Fe+2 by oxidizing iodide ions, and then gets oxidized to Fe+3 by reducing persulfate ions. Now let's look at the formation of interstitial compounds by these elements. Interstitial compounds are compounds of indefinite structure and composition. They are formed by the incorporation of small atoms like hydrogen, boron, carbon, or nitrogen in the spaces between the metal atoms, that is, the interstices of the lattice. The component elements of these compounds do not combine in definite ratios. Hence, these substances are also known as non-stoichiometric substances. For example, Fe0.940, TiC, Mn4n, Fe3H, VH0.56 and TiH1.7. Note that the formulae do not correspond to any normal oxidation state of the metal. The important physical and chemical characteristics of these compounds are: they are extremely hard. Some borides approach diamond in hardness. They have higher melting points than those of pure metals. For example, titanium carbide melts at 3683 Kelvin and titanium nitride melts at 3473 Kelvin. They are chemically inert. They possess good electrical conductivity. Let's look at the alloy formation by these elements. Pure metals have poor mechanical properties. Hence, they are not used as such in industry. The properties of the metals may be modified by adding other elements. Alloys are one such class of compounds. An alloy may be defined as a homogeneous mixture of a metal with other metals or metalloids, and sometimes even a non-metal. The atomic radii of the transition elements in any series are not too different from each other. As a result, they can very easily replace each other in the lattice, and thus readily form alloys. Alloys are classified according to the components in two distinct types, namely, ferrous and non-ferrous. Ferrous alloys contain iron, carbon, and one or two of the other elements like chromium, vanadium, tungsten, and molybdenum. When the content of carbon in an alloy is less than 0.1%, it is called an iron alloy. When the content of carbon is more than 0.1%, the alloy is called a steel. Depending upon the other elements present, steels are classified into several types, like vanadium steels having vanadium, chromium steels having chromium, and so on. Non-ferrous alloys are alloys that do not contain iron as one of the components. The number of non-ferrous alloys used in technology is very large. Aluminium alloys like aluminium bronze, duralumin, and gamma alloy, along with magnesium alloys like magnalumin and electron, find numerous applications in various fields. Similarly, brass, an alloy of copper and zinc, and bronze, an alloy of copper and tin, are also important non-ferrous alloys. The table shown here lists some important ferrous and non-ferrous alloys along with their composition and uses.